she will introduce the rest of the panel. Thank you very much for starting the recording, Isabel. So it's a pleasure to welcome everybody back for the second part of today's session. Apparently my internet is unstable, so hopefully people can still hear me. So I'm Elahi Mandel, I'm the chair of ANITA, and it's a great pleasure to welcome you back. Our next session is organized by Isabel Romero-Shaw, who is one of the members of the ANITA steering committee. Isabel is also a PhD student at Monash, doing some very exciting work in gravitational wave astronomy. And from what I understand, given the very impressive set of publications coming out of that, none of her cycles are going to waste. So congratulations, Isabel. And now Isabel is going to introduce us to the really exciting speakers and panelists we have in store for the next session. So over to you, Isabel.
Thank you very much, Ilya, for that glowing review of my publication list. It's very kind. Okay, so it's my pleasure to introduce today Dr. Adam Stevens, who's going to be talking to us about this work he's been doing on the imperative to reduce carbon emissions in astronomy. This is really, really important. And if you haven't read the paper that Adam wrote, or the paper that Adam led, which is a perspective article in Nature Astronomy, which it has the same title as is written on his slide here. It's well worth a read, very eye-opening, and I'm really looking forward to hearing this talk today. So take it away, Adam.
Thank you so much, Isabel, for the invitation to talk. So good afternoon, kia ora to everybody who can join us. It's an incredible pleasure that I get to dial in via Zoom from Wajak Noongar country in Western Australia. Yeah, so this talk is going to touch on the subject of climate change. It's going to touch on what we are doing to contribute to the problem, unfortunately, and what we can do instead to contribute to the solution. And at the end of this talk, we're going to have a panel discussion. We've got some other exciting people joining us for that, who I can see are all in attendance, but we'll get to that in a moment. So I first always need to start these talks by giving a global perspective on climate change. This plot here is from data that anybody can download from the relevant US authorities. This is the National Oceanic and Atmospheric Administration. So you can literally just download these points and plot them yourself, which is exactly what I've done, which shows the temperature change on average across the globe relative to the start of the Industrial Revolution. And so it's pretty easy to fit a curve to these points. And as you can see, it's well described by an exponential, showing that our temperature is rising as a result of human activity. And with this rising temperature comes rising sea levels, which leads to the mass displacement of humans, which is, of course, a humanitarian crisis, the extinction of species, which is itself a biological crisis, and food shortages, etc. The potential significance of these things that can transpire or will transpire as a result of global heating cannot be understated. Right, so what's causing that heating from taking place? It's our emissions of fossil fuels, which is normally quantified in terms of equivalent carbon dioxide mass, because carbon dioxide happens to be the most prevalent greenhouse gas in the atmosphere, and one that is readily produced from the burning of fossil fuels. So this plot here from the Global Carbon Budget, which is a paper that gets updated, or there's a new version of the paper that comes out every year, which summarizes global emissions and where they're going, shows you that as we have that exponential increase in temperature, we also that's strongly correlated with an exponential increase in CO2 that we're pumping into the atmosphere. Although that CO2 doesn't necessarily stick around in the atmosphere, there are three natural sinks on planet Earth for where that CO2 can end up, which you can see on the sort of the negative side of this graph. So that CO2 can end up in the ocean, it can end up in the land, or it can remain in the atmosphere. So the stuff that remains in the atmosphere is what causes the greenhouse gas effect. The stuff that ends up in the ocean is very problematic for other reasons. This increases ocean acidity, this screws up the currents in the ocean, which is what naturally regulates the temperature of the planet. So you actually have compounding temperature effects that take place as a result of this. And it also means that the effect of climate change is not uniform across the globe. So some places will experience it a lot more than others. And of course, it screws up or messes with weather patterns as well. Okay, so as of 2019, which is where the data from this paper published last year goes up to, if you take the total amount of emissions from the planet and divide it by the number of people on the planet, you end up with an average of about 5.5 tons being emitted per person per year. I prefer to divide by the total number of people that you can actually claim as being responsible, i.e. not children. I don't think it makes any sense to average over children. So if you just divide by the number of non-dependents, which is typically defined as people aged 15 and over, your number's more like 7.3. Okay, so that's the global context. Let me give you the Australian context as well. So again, you can just go onto the Australian government website and pull down these data and plot them yourselves, just as I have done here. So this is looking at Australia's emissions over the last 2 decades. And there are 2 lines here. One is for the total emissions, and one is that one where you exclude emissions that are associated with land use change and forestry. So the blue and cyan you can think of as actually being the fossil fuels that are being emitted. And so there's an emissions value associated with land use and land use changes. You can think about the clearing of forests, for example, or replanting of forests can actually give you a negative emissions, because then you're actually doing something to pull CO2 out of the atmosphere. So this is why it's possible to have the total lower than the excluding one. A lot of the time when you hear governments talk about Australia's emissions having declined over the last 10 to 15 years, they're referring to the total, but actually the amount of fossil fuels we've been burning as a country has had a steady increase over the past few years, although it's relatively flat, as you can see from this plot. It's starting to go down now, but whether or not that's a long-term trend or whether that's just pandemic related, I don't know. But you'll notice that number is a lot larger than the global number was. So in Australia, per non-dependent, we're responsible for about 25.5 tons of CO2 equivalent each year. Okay, so that's more than, well, what is that? 4 times roughly what the global average is, a little bit under that. Okay, so many of you will have heard about the Paris Agreement. This is an idea to try to limit the amount of global heating to between 1.5 and 2 degrees Celsius, ideally below 1.5. But the thing is, in order to achieve that goal, there has to be a rapid and continual reduction of emissions from now. And when I say now, what I actually mean is yesterday. And when I say yesterday, what I really mean is we should have already been doing it for several years, but we haven't been. And to illustrate this point, I'll show you another plot here from a paper a few years ago. This is again just showing cumulative, emission rate as a function of time on the left and cumulative emissions as a function of time on the right. So it's that same data that I was showing before, actually, in the cyan here is the total global emissions. And there's breakdown of other things there, but just focus on the cyan one for now. Right, so this is published in 2018, which means anything thereafter is essentially a model for how the temperature of the planet might change if we were to decrease our emissions. And this is one, the curve after that 2018 point is one way that we can keep within that 1.5 degrees or 2 degrees warming per the goals of the Paris Agreement. Right, so this line indicates roughly where 2021 is in the present. So we should already be decreasing our emissions significantly. And we should already have a negative gradient there, but we don't. We're still on a positive gradient. And every year that we spend not transitioning from a positive to a negative gradient, it actually decreases the amount of time that we need to get down to 0 to achieve that 1.5 or 2 degrees only of warming. And realistically, what that means is that we just won't achieve those goals. Okay, so that's the world in context. So what about astronomers? We're all citizens of this planet. We're all contributing to this problem in some capacity. Is there anything that we do in our jobs that might be contributing to this problem more than the average person? Or are we like average people? Who's quantifying this? What are we trying to do about it? These were all questions that we were throwing around at a quarterly lunch with postdocs at ICRA in June of 2019, which is where all of this stuff for me started. It was just a lunchtime conversation with my peers. You know, this is a subject that I've had in the back of my mind for a long period of time. I've known about climate change. I've known about the importance of reducing emissions, but I've never, you know, up until this point, I'd never taken the time to sit down and quantify what that means. And, you know, we all have a high level understanding of the physics of these things because it's part of our training as students. But I'm guessing many of us haven't taken the time to actually read literature on the subject. So I took it upon myself to actually, you know, dig into some of this stuff. So from this meeting, we thought, you know, we should really ask senior staff, like, is anybody monitoring what our emissions are? Do we have policies surrounding this to try to keep our emissions to a minimum and so forth? And so I just happened to be the postdoc at the time that we had this meeting. So I took this to senior staff, which was well received. So that was, yeah, still in June of 2019. And there was tentative agreement to start sourcing data. At the time, we thought the thing that we should focus on is our flying habits. You know, pre-pandemic, we were flying around the world like crazy. I know I had like my track record of a postdoc in terms of how much flying I did prior to the 2019 is terrible in the sense that it was very large. So I thought this would be the worst thing, and to spoil the results that are coming up in a moment, it turns out it's not. At any rate, as we started collecting these data and conversations continued to be had at the Institute, it turned out to be quite timely because this is when the decadal plan for Australian astronomy, the midterm review was being written for the decadal plan. And so there was an idea to bring sustainability into that. And so I was invited to be a part of that. And we had a very short time frame between October of being invited to then December of having a paper drafted and submitted on this topic that actually assessed the emissions in Australian astronomy. So this was the team of people I put together. I ended up leading it by default, basically, because nobody else took the opportunity to. There were other people who could have. So Sabina Belstedt, who's another postdoc here at ICRA UWA, Pascal Elahi, who is joining us for the panel session afterwards, who was at the time also a postdoc at UWA. So the three of us were, you know, a part of those same conversations that started this whole thing. And Michael Murphy, a professor at Swinburne University of Technology, who has a strong interest in this subject area as well. So the project that we set out to do within that time frame was to, you know, assess the sources of emissions that we thought were relevant for astronomers. These were the four that we targeted: flights, the powering of observatories, the powering of supercomputers, and the powering of our offices. We thought that this would cover all of the big ticket items. And it may well be that there are other things on top of this that we haven't considered, but we wanted to limit the scope to what we do within the frame of our jobs. So not getting to and from the workplace, that sort of stuff, because that's kind of outside of work hours, so to speak, but all the things that we do when we are normally at work, which doesn't have to mean physically at work, of course. So to cut a long story short, this was the result of what we found. We have actual data on all of these things here, which is why we can quantify errors in some capacity, although, you know, these aren't formal confidence intervals that you see on these bars. But it turns out that supercomputing was by and large, the biggest source of emissions for astronomers. Not only that, but when we summed up all of these sources, we found that just the job of being an astronomer, on average across the country, was resulting in 37 tons of emissions per year per full-time equivalent person. So that's about at the time, it was 40% greater than what the Australian average was for work and life combined, right? So all of the stuff you do, if the average Australian does at their job and at their home, in their personal lives, etc. Just our jobs alone, we're 40% higher than that. And this is something like 5 times what the average person globally would be responsible for. So that was a confronting number, I would say. It's sobering in a way, but not in a pleasant way. And so it made it pretty clear that we needed to do something about this. Now, as the purpose of this meeting is green computing, I'm only going to focus on the computing aspect for the rest of this talk. If you happen to have questions about the other components, those can maybe come up in the discussion panel. But I think we should keep computing the focus. So just to tell you a little bit about how we came up with that figure, what we got was actual data from Pawsey on how many CPU hours had been consumed over the course of an 18-month period, of which we only used 12 months because we wanted to make sure that there weren't, annual, not annual, natural fluctuations within the year about usage. Right, so we had total number of CPU hours, and we also have the total amount of energy that the facility consumed. So I'm not just talking about the amount of energy that runs through the processes, I'm talking about the facility as a whole. So if you take the number of core hours that were run and divide it by the total power that was consumed, you figure out that on average, including all overheads and the entire covering of the facility, for every core that you use at Pawsey, you're effectively consuming 53 watts of power. Now, as part of the midterm review of the decadal plan, there'd also been a rough assessment of what the total computing needs of Australian astronomers was, because we had to extrapolate from the data we had from Pawsey, because this is only one facility and we use many facilities across the country. So if we take the estimate that as a national community, we're using about 400 million CPU hours a year, and also combine that with Australian government figures on what the emissions per kilowatt hour are in each city, and we average over the cities that we know the supercomputing facilities that we use are at, then we have a figure for an average figure for the amount of emissions per unit energy. Okay, combine that with the CPU hours per year and combine that with the power per core, that then allows us to calculate a total amount of emissions each year. So that's how we came up with that 37. Sorry, the 37 was for the total. That's how we came up with that 22 tons per year average. So it's, astronomy is a major sink of supercomputer time in Australia. We're not the only industry, is not the right word. We're only, there are many other fields of research and many other industries that use supercomputing time, as we heard about in the first session today. But we still make up a pretty significant part of supercomputer users in the country, if you like. So at Pawsey, for example, we're responsible for at least 25%, because radio astronomy alone consumes 25% of the resources there. And this annual report is a year outdated, but I've looked at the numbers for their most recent one, and it's pretty much the same. Okay, so how is that split across the country? Well, roughly speaking, based on that estimate that we had within the decadal plan, we figure that about 40 million CPU hours are being consumed at AusStar by astronomers. About 80 million are being consumed in Western Australia. So this is mostly at Pawsey, but some of that's now also at DUG Technology. About 120 million across NCI in the ACT, and then about 160 million are being consumed overseas. So it's easy to figure out what the emissions are in each of the states and territories in Australia, because we have figures for that. The overseas stuff's really hard because we don't actually know how that's distributed across countries and cities, and what it's a bit of a fact to figure out, even if you know where all of those places are, what the relative emissions are. It can be done, but we didn't have access to that information, certainly not within the timescale that we were working with. So each of these places has a different rate of emissions per unit energy. So this is how the graph changes if we go from time to emissions based on that amount of time. So actually energy out of the states and territories shown here, energy in Victoria is actually the dirtiest. which is why that contributes, it over contributes based on the time. We didn't, as I say, quantifying for overseas is tough, so we've just done this based on an OECD average, but that has a pretty significant error on it, which is the main source of the error bar we saw on the bar graph before. Okay, so that's where those numbers came from at the time. Now, bear in mind, this was done in 2019, which means that we were operating from data from 2018. So stuff has changed since then. Okay, so since we put this paper out into the public domain, it was picked up really promptly. I posted it on arXiv the day before going on leave, and then I think a week later, once I'd resurfaced to the world, realized I'd missed a whole bunch of emails from journalists wanting to write stories about this, which they had to write without any comment in the end. So be it. But what's been really good is that this has also led to further discussions taking place at the European Astronomical Society meeting, for example, last year. And it's also been a driving force in some sense within the Astronomers for Planet Earth group, which is a group that I was connected with, I guess, as a result of this, essentially. And through that meeting and through that organization, we ended up doing more. So there were a series of companion papers that were written from people in various countries along similar lines, not exactly the same topic as what I'd led for this white paper, but assessing various aspects of how astronomers are contributing to climate change and how climate change actually affects doing astronomy. So there was a special issue of Nature Astronomy that was put out in September last year, which has been dubbed the climate issue. We didn't make the cover because we didn't really have any pretty pictures to put on the cover, but it does seem to be the main focus of that issue. And I highly encourage you guys to check out all of the papers that were in there. Most of them are really short. Most of them are only like 2 or 3 pages, so they're very digestible. My one's a bit longer. So one of the things we learned from those companion pieces is that being an astronomer in Germany is a lot greener than it is being in Australia, which is not really that surprising when you consider the fact that most of the power that goes into Australia's grid is from fossil fuel burning, and most other countries in the world don't do that because that's just not a sensible thing to be doing in the modern age. There was no clear differences between what the requirements of an astronomer are at the MPIA, for example, versus what they are at ICRA. Like, there's no discernible systematics at play there. It really just came down to how much energy was required to power the computers and the observatories that we use. So they were half, I think, or maybe even less, just reading off this graph, yeah, less than half of what we consume. I will say, though, that they inflated the values for flights, and there are reasons for this to do with quantifying the effect of altitude with emissions, because that's a difficult thing to quantify, and it actually changes the amount of effect of global warming that causes. Okay, so slightly more on the specifics of computing. Another one of those companion pieces looked at the ecological impact of coding practices. This plot is a bit busy. I've tried to put the bullet points from the things that I took away from that paper on the left-hand side. But the idea is, it's, you can make a simple graph of how long it takes to complete a problem that you need a computer to solve versus how much CO2 that produces. And really this y-axis is just how much energy is consumed, right? And then that's just a one-to-one relation with CO2 production based on what your local power supply is, or where your local power supply comes from, I should say. Okay, so some jobs scale linearly. The longer, if it's a similar type job, the longer it takes to run. If it takes twice as long to run, it should require twice as much energy and therefore produce twice the amount of emissions. But it matters what your coding language is. If you're coding with high-level languages, there are greater overheads. So the same amount of time you spend running something, or the same job that you want to run, is actually going to produce greater emissions than if you're coding in a lower level language, something that's more akin to how a computer actually interprets things. Something I hadn't appreciated before is that multi-core processing is actually far more carbon intensive for a fixed task than single core processing. And you can see that from the green line here. So the idea is that for a fixed task that is parallelizable, obviously if you only run it on one core, it's going to take a long time to run, which is why it's so far to the right on the x-axis. But if you increase the number of cores and thereby decrease the time it takes to run, the absolute emissions you produce, and meaning the absolute energy that you consume, increases. So just to clarify, that's not the amount of energy you use per unit time, it's the absolute amount of energy that you've used once the task has been completed. So where you get temporal efficiency in your code, you might actually be making your code less efficient when it comes to emissions, or more harmful to the environment, which is a concern, because then now you've got a conflict of interest when it comes to optimizing your code. Do you optimize it for time and for financial resources, or do you optimize it to reduce emissions? Similarly, if you use faster processors that are even in a single core setting, so ones with higher clock rates to do the same task, the absolute emissions you will produce by the end of that task are greater. And also, if you're using virtual cores rather than physical cores, they also produce more emissions for a fixed task. So these are all interesting things that are things I think we should be considering when we're running HPC jobs. And I don't really know what the solution to this is, and this is hopefully something that we can discuss a little bit more about towards the end. Okay, so let me come back to this thing I showed you before, because I said that this was based on 2018 data, and things have changed since then. So what's changed since then? Well, we kind of don't need to worry about Victoria and ACT anymore. And the reason for that is that Swinburne has procured 100% renewable energy to cover the energy requirements of its campus, and that includes the AusStar supercomputer. So they have essentially funded a wind farm that didn't exist before to now be pumping as much energy into the grid, or maybe more than what the campus consumes. So this isn't a direct line from new renewable energy to the university campus, but it's going into the same grid that Swinburne's pulling from. So they're net zero in the emissions that they're producing, which is awesome. And it's really important to emphasize that so let me take a step back. One way that you can have a net zero emission supercomputer is through this explicit purchasing of renewable energy. The thing is, if that renewable energy that you're purchasing isn't new renewable energy that's been putting into the grid, then it actually doesn't make an overall difference as far as the planet's concerned, right? It doesn't care who's responsible for the emissions. It only cares whether the emissions are taking place or not. This is an example of where more renewable energy has been pumped into the grid. That's what needs to happen. The ACT as a territory actually produces more renewable energy than energy it consumes, and it shares a grid with New South Wales. And the reason for the number being so large before, I can just go back to the reason why this number was so large before is because the government figures tell you that, oh, well, the ACT and New South Wales are part of the same grid, so the emissions that you get for a kilowatt hour of energy are the same in those two places. And in some sense, that's true, right? Because if you picked up the national computing infrastructure from Canberra and you shipped it to Sydney, and then you plugged it in, that actually would have zero effect on the amount of emissions that Australia produces. It wouldn't make a difference. But because it's in the ACT, its power requirements have been taken into account by the territory government when they've had to calculate how much renewables they need to produce to put into the grid to balance out what their energy requirements are. So I think it's fair to say that that's a carbon neutral facility, although it's not always as black and white as that. Okay, so those were the figures before. With renewables as of 2020, we've cut down the emissions from supercomputers a lot. I just haven't updated the slide since 2021 because I don't have any new information other than that at this stage. Of course, with a pandemic, we don't have flights, so that problem is solved as well. And let me encourage people, when the pandemic is done and we're back to being able to travel, consider when and how you travel, because we've accidentally solved a problem here. I'd encourage people not to just go back to the old norms and therefore bring the problem back. And we can actually eliminate all of this if we just have fully renewable energy everywhere. and I really want to highlight this as the key. Where your energy comes from is what matters the most. You can make your code as efficient or as environmentally friendly as you like. You can keep increasing it by factors of 10 in terms of efficiency, but you'll never efficiency your way to 0. And I've definitely stolen that as a quote. Those are not my own words. At the end of the day, you have to get the energy from the right places. It has to be from a renewable source. So that's the #1 most important thing that we should be doing as a community, is making sure that the energy we need for the facilities that we need to do our jobs, which are very energy intensive, are coming from the right place. I mentioned the Astronomers for Planet Earth group a couple of times. I would encourage anybody who's interested in this topic who hasn't already joined the organization to join the organization. We've become quite large in the last year or so. We're now up to close to 1,000 members across many different countries. And you will have also seen that we put out an open letter earlier this year, which has now been signed by more than 2,700 astronomers from 73 countries, where we're basically calling on all astronomical institutions to take this point seriously, that we need to get renewable energy powering our facilities as soon as possible, because without doing that, there's an ethical question surrounding our research, and it's not unique to our research, right? It's the same ethical question that goes to anybody who's doing anything that requires electricity. But it's still something that we need to grapple with. And so we really feel that this needs to be placed as a priority. If you haven't signed this letter already yet, you still can do that. And we're also asking for institutions to sign on to that. So if you want to put pressure on your institution as a whole to sign, that's also something that can be done. So more good stuff in terms of what's been coming as a result of all this work. And sorry, when I say as a result of all this work, I'm not trying to take credit for any of this stuff or anything. I'm just, it's all kind of progressing off each other, and it's all building, which is great. That's all I mean to say. So there's another session at the European Astronomical Society meeting this year. I'm not involved in this, but 2 of our wonderful panelists who are about to chat with us are. I recommend signing up for this if you like. It's all online. I was involved in this session last year. It was absolutely fantastic. It's one of the best conference days I think I've ever had. I learned so much about this subject and more. And it's nice to step away from astrophysics and just think about what astronomy means as citizens. And that's where I'll end. Bonus points if you know where the meme comes from. That's it.
Thank you very much, Adam. Does anyone have any questions? That was a really brilliant talk, by the way. And also, if anyone knows where this meme comes from, please put a note in the chat, because I have no idea. So I have a brief question while other people are gathering their thoughts, which is, how do we sign up for that meeting that you were showing on your previous slide?
Presumably by going to the appropriate website. Is there a website on there? I don't know. I can. Oh yeah, there you go. EAS.
That one, yeah.
unige.ch.
Great, thank you. Somebody's guessed Game of Thrones.
No.
I think I would recognize it if it was Game of Thrones.
I think it's from before the books were even written.
So we've got a lot of guesses for the meme. If I just scroll up, so there were some comments during while you were talking.
Oh yeah, someone's got it. Robin Hood Men in Tights. There you
go. Good. So there was quite a few comments while you were talking about why. So for multiple cores, you end up having orders of magnitude more carbon emissions than you do for a single a single core. So Pascal has commented on this, but I think there's still some confusion.
Sure. So I'm not an expert in this, but my very naive understanding is that the more cores you have, the more overheads you essentially introduce, the more talking parts of computers have to do to one another. So I guess there's more energy consumed in there, but perhaps Pascal wants to jump in and say more.
Yeah, I guess I can comment on this because I've been replying back. It is, I like the paper. I think that point is actually a very misleading point because a problem you can run on one core you would never necessarily run on many cores. And so, yes, there's extra stuff of like, okay, you have to power the communication that goes between the cores. They have to be heated, cooled as well, because now you're normally doing a hard problem. They're going to be at a high energy state. So there's cooling, there's powering the network, there's powering also all the hard drives that have to live with the system that is obviously going to produce lots of data, et cetera. There's an enormous amount of overhead. But then, as I said, the realistic comparison would be if you had a one core problem that could be run by one core in a certain amount of time, it would take an enormous amount of time if you could actually run on millions of cores, because there's no memory. That any problem that requires that many cores has to have usually like a very large memory footprint. This would never fit on a laptop. You'd have to have some specialized memory. You'd have to power all that memory. You then have to power all the communication between the memory and that single core running on a single CPU. I'm maybe being too harsh, but I think that point is really misleading, and no one should use that point to make anything out of anything. It's an apples to orange comparison. It's not appropriate.
All right, trust the experts.
It's kind of interesting to think about, but it's probably not something that you should really take as, okay, if I run something for longer amounts of time, my footprint is lower, because you don't know that that's necessarily the case, and the problem may also not even fit on one core. It's like when would you ever run something that needs 10 million, like a million cores that you could do with one core in a couple of seconds or like hours? There is no problem. It's massive overkill unless it's not feasible. So, and Nikhil brought up one good point, is that there is, I mean, unless you're running on a very old CPU that only has one core on it, most CPUs have multiple cores. So if you ran on one core, that CPU is also in a very low energy state, not consuming, probably not even heating anything, right? If you can do it on your laptop with one core, it doesn't generally produce that much heat. And there's not usually that much memory flow back and forth. So there's lots of stuff. I hope that's informative for everybody.
Thank you, Pascal. Nikhil, does that answer your question, or are you still having some confusions?
I think Ilya's got a hand raised.
Yeah, Nikhil says he can ask offline, so I think he's going to go
cool.
ahead and do that. Ilya, go ahead.
Yeah, so I had a question. Do we need to worry about fixed sunk costs in addition to running execution costs? So for example, it doesn't matter whether you're using renewable energy or not to run your center, if it costs a lot of if you produce a lot of carbon in the process of building that center, or in the process of building those computers, that's sort of a fixed cost, right? So are those insignificant relative to the cost of actually running the center or the cluster?
That's a really good question. Okay, so let me see if I can reframe that question slightly. So let's say hypothetically we've got a supercomputing center that is just pulling power from the grid, and that grid happens to be some dirty energy, some clean, and there's a plan to build, let's say, a solar farm or a wind farm to dedicate energy towards that facility. Then what's the environmental impact of building that new facility, and over what sort of time frame would you break even, so to speak, from running that facility? Is that a fair way of rephrasing the question?
Yeah, I think that's part of it. I was also thinking in terms of building it costs some amount of carbon to build the actual computers.
For sure.
Build the facility, the supercomputing center itself. But yes, building the renewable energy facilities obviously also has a fixed cost. So sort of all of that combined, I'm just wondering, is that obviously negligible relative to the cost per hour of operation over the lifetime of those computers and those wind farms and so on?
Yeah, look, I haven't done a thorough analysis of this, if I'm being entirely honest. My intuition, and based on conversations that I've heard from other people, and I've heard some talks from people in the SKA about this as well, is that the sunk cost that you have in setting these things up is small relative to the ongoing cost if you're running a facility like this for several decades, which is what you would expect to do. Cost hasn't cost to the environment. So I don't know that it's obviously negligible, but I'm pretty sure it's less, is my best answer.
got it. And I see that Paul is also agreeing with you. So thanks very much.
Okay. Does anybody else have a question specifically for Adam? If not, I think now is a good time to move on to the panel discussion section of this afternoon. So I would like to introduce our panelists. So you've already heard from Pascal. So Pascal is a high performance computing specialist at Pawsey Supercomputing Center. And he was a postdoc before, and he was doing the simulations of entire virtual universes within supercomputers. So he's grappled a lot with supercomputers in his time, I think it's fair to say. We also have Dr. Vanessa Moss, who is a researcher based at CSIRO Space and Astronomy, and she is head of science operations for the ASCAP radio telescope. And our fourth panelist is Dr. Natasha Hurley-Walker, who is a multi-award-winning radio astronomer, who has created a low-frequency panoramic view, radio panoramic view of the universe, and shared this image in a popular TEDx talk. So it's a very exciting panel, and I'm hoping that our panelists can tell you a bit more about themselves in their introductions just now. So my first question to you all is, please tell us a little bit about yourself and how you became interested in making astronomy greener, and also what kind of work you do to promote sustainability. So I would like to throw this question first to Vanessa, I think, if that's okay.
Thanks, Isabel. Yeah, sure. So I have a few very quick slides to go with this introduction. So I'll just try and get that kicked up onto the screen. I have clicked share. It's thinking about it. Did it work?
Yes. Thank you.
Okay. Wow, it like hung for 10 seconds. Okay, so I'll just use this to very quickly introduce myself, what I do, and my connection to sustainability. So firstly, who am I? I'm based at CSIRO. You may not have heard, but we actually just changed our name. So we are now CSIRO Space and Astronomy, and it kind of abbreviates to SNA. So that's just a recent thing. I've been based there for 2 years. Prior to that, I was in the Netherlands at Astron, which is sort of like, in a way, the CSIRO of the North, sort of like, so, you know, the Dutch version. And they also work within a collection of institutes that are all science focused as well. In CSIRO, I have a few different hats that I wear. So as Isabel mentioned, I'm the head of ASCAP science operations. This is really in terms of taking care of what the science observations get done on the telescope. So everywhere from specification and what the science teams need to the point where it reaches Pawsey. That's the kind of main realm of influence that I have. I also manage the duty astronomers for the compact array. So this is about how we train people and support telescopes. And there's interesting conversations about what training looks like in the future as well. So we can, you know, can we make it more location agnostic than it's traditionally been? And in this context, I'm the ongoing chair of the Future of Meetings Organizing Committee. This was a symposium we did last year, but it's actually with ongoing relevance about how people can be more digital first, and that ties into how they can also be more sustainable. So very quickly about the conference itself, it was really focused on how we can do better in how we meet. The reason that's related to sustainability is because that was one of our key themes. We were interested, like, you know, Adam said in his talk, we should be aiming to reduce the travel and think carefully about how and when we travel, because we kind of had this, I guess, approach of we would just travel because we could, sort of, and it's more, you know, there's an growing importance of being more socially responsible for this, and Europe is already doing it. So even if we chose not to travel less, the rest of the world is going to choose to travel less to see us. So it's actually in our best interest to adapt the ways we meet and the way we interact to make sure that as a very isolated, big country that's far away from a lot of the rest of the world and in not necessarily the most convenient time zone, that we adapt in this way. So what did we do with TFOM? It was really about experimenting. It was about exploring this space and searching for best practice in terms of meetings, really leveraging technology. Technology was the key, and we did a lot ourselves. And I think that's something you see a lot in astronomy, is that we tend to take a lot of ownership in what we do, you know, conferences or workshops or stuff like that. And I think that's transitioning from that into something that becomes more sustainable for big conferences as well, where traditionally event management and in-person venues have been a key aspect, is something we're still exploring. And then the impact of also social online. So how do we connect with people in meaningful ways and emulate those hallway conversations that everyone talks about? I mean, it's particularly relevant for us in CSIRO because we're in space and astronomy, because we're split between Sydney and Perth. So if the way we work depended on physically traveling or the hallway conversations, then Sydney and Perth are just going to grow further and further apart. I wanted to mention we do have this legacy archive. I'm going to put the link in the chat in a sec, and all of the links in the PDF are clickable, but you can go check out the talks. You can see that some of the talks focused on sustainability specifically because it was one of our key themes. And we're continuing to update this website as we do more activities in this space. And there were specific outcomes. So we wrote a report that covered how we put the conference together and what we learned and what our recommendations were. And again, since sustainability was one of our key elements, we focused on ways of addressing that specifically, but also if you travel less. I mean, we're coming at it, we can't necessarily change how people use supercomputing or renewable energy usage in astronomy, but we can, you know, encourage people to collaborate differently and to adapt the ways that we meet and collaborate. And we also have a Nature Astronomy comment on the topic as well. So what are the implications for sustainability in this context? I think the three key ones are, we can adapt the ways that we meet and collaborate. And these are things that we can do on an individual level, as well as, you know, at the institute level and how we conduct astronomy research across Australia. But it's also about the accountability increasing at the institution level. So sustainability being a core part of what we do and becoming part of our policy. It doesn't mean we never travel. It doesn't mean, you know, I'm never going to see the people in Perth ever again. It means if we do it, it has value. There's a reason I'm not going over to Perth to sit in a room on a telecon, right? It's about just changing it, making sure there is valuable and having that flexibility, and also carbon offsetting in a responsible way. And I think one of the key things also in this context is ensuring that EMCRs are not affected negatively, because the culture of how we've done astronomy is, you know, has involved a lot of travel, and we need to make sure that it's still easy and supported to build careers and network, even if we switch to more digital mechanisms of doing so. So those are just some of the thoughts that I wanted to bring into the discussion. I'll stop sharing.
Thank you very much, Vanessa. Shall we go to Pascal for his introduction now?
Yeah, so hi everybody. I, like Adam, am talking from the Wajak Noongar lands. I'd like to pay my respect to the elders past, present, and emerging. I used to be a computational astrophysicist, so I obviously had lots of experience doing computing and trying to use supercomputers. And I remember at very early stages of my PhD, I mean, I never really thought about it, right? It was just kind of trying to run and get a big simulation and look at it and do some interesting science. And like Adam, I just started thinking about like, well, what was the impact? And I also, like Adam, was surprised that computing was such a big portion of our carbon footprint as astronomers, and generally probably of all scientists. So I mean, I thought flights would be probably bigger, but I expected computing to be high up there. And I'm glad that Adam showed that plot, which showed the scaling of CPUs, because this is kind of where I'm kind of going to talk about in terms of my presentation. So let me just share my slides. Here we are. Okay, so green computing. So to give people some context, POSI is undergoing a refresh in its systems. And the lifetime of a lot of supercomputing centers are roughly 5 years, maybe. So usually supercomputing centers try to refresh their systems using new technologies roughly over 5 years or a few years past that point. And POSI has undergone a capital refresh, and they have a new system called Photonics, which is named after the Latin name for quokka, which is why you see a quokka on the screen. And so the main thing I'm going to mention is where computing is heading, because it is a big deal, but it does require rethinking how we start doing computing. So to give you some context, so Magnus is the POSI supercomputer, It's a CPU-only supercomputer, so it's a, if you will, standard technology. You can imagine trying to take your code that runs on your laptop and trying to maybe make it scale on Magnus. Magnus uses Intel CPUs. There's about 12 cores per CPU. They run very hot though, right? Because it's a supercomputer. They're meant to run at like 90% capacity all the time. So these CPUs are meant to be turning over instructions all the time. There's about 64 gigs of memory. The idea is it's about a petaflop or 1,000 teraflops. And though this is a technical term, it does make use of a very particular type of instruction set to make codes run fast. And I'm talking about low-level languages like C, Fortran, C++. It's basically impossible to get high-level codes like Python, even though everybody loves Python, or R to run fast. The goal is to try to not use that and use that as an interface for running stuff that uses like compiled codes. The new machine has quite a different set of architecture, and there's a reason why we're doing this, and it's the reason why I'm going to mention this in the context of green compute. So it has CPU and GPUs. So GPUs, right, graphical processing units used in gaming, can obviously be used to do compute. And photonics will start off at around roughly just CPU only, a new technology AMD cores. They run a little, they're a bit more energy efficient, or reasonably more energy efficient than the current system, just the CPU cores. And they'll be about 2.4 petaflops, so 2,400 teraflops in that. And they use some similar sort of sets to make things go fast and run efficiently. But most of the compute, about 40 petaflops of the new system, is all GPUs. Right, so you have to think about not using a CPU and trying to work out how to use this GPU, because most of the compute lives there, and there's a reason why most of the compute lives there. It's not just because we thought GPUs are cool. There's a very specific reason why. Let me. I'll skip the details of photonics. I can go back if people are interested. It has to do with this. So on the right-hand side is the green 500, essentially HPC systems, right? So the greenest CPU systems. As opposed to normally people want to try to get into the top 500, just in pure compute. And there's a very interesting set of lists there. So there's a couple of systems that are not particularly powerful, like teraflop systems, but the big ones, there's number 2 and number 6 that I've highlighted, are in the petaflops. So 27 petaflops, 35 petaflop range, and they all use GPUs. And the energy efficiency of running compute on, let's say, something that's Magnus, just kind of generic CPUs, you get about 2 gigaflops per watt that you spend doing some compute, where photonics will be 20 gigaflops. So it'll be order of magnitude more flops, more calculations that you do, more floating point operations per watt that you spend. Suddenly you're looking at way more efficient systems. And I mean, the new machine at POSI will be, we should be in the top 500 of the green list. So it'll be one of the greenest systems out there that offers petabyte scale, tens of petabyte scale compute. But that change requires rethinking how you actually start coding up stuff, because now you're talking to try to figure out how to use a device that's not a CPU, and does require changing how you do your compute. And that's where we're going to try to really help users be greener. So it's not just that our system is greener. If you just gave you your system and you tried to take your code, you're not going to use the system efficiently. And so then you're not going to be green. You want to be able to use the system as most efficiently as possible to reduce the amount of compute time you have, but also then consume the less, very little energy. And to do this, to kind of really get people to start using this and thinking about energy efficiency, we are running uptake projects to try to help users understand the bottlenecks in their code, how to migrate their codes to GPUs, how to make use of parallel I/O, something that I haven't mentioned, but hard drives are energy sinks. If you have to write and read a lot, they consume lots of energy. So then you have to cool them. They generate heat, but they also have the system consume lots of energy, and then you have to provide that energy. If it isn't clean, green energy, then you want to reduce your energy consumption. And to get people starting to think about this, we are trying to set up a system where if you submit a job, it doesn't just tell you your job is run, it's used this many core hours. We tell you this is how much energy it's used. This is how efficient it was. To help our users identify, my code is running inefficiently, is using way too much energy per watt. I can get a lot better. I can get a time to solution that's shorter and also consume less power. The goal is to write faster codes that not only use resources, but allow for new, bigger jobs to be run, right? So something you could never run on a single core, no matter how much time you were given, to something that you can now run because you're using, roughly maybe 100,000 compute units, right? Something that's can't do at all, and now you can do green. You can do it as efficiently as possible and also do it quickly. And that's the goal that POSI is trying to push, and that's how we're trying to help the environment by trying to really make green compute and also computing efficiency to really push this, to get users to start thinking about this. And I'll end there, and I'll pass on to Natasha, I assume.
Hi, everyone.
Yes.
Can you see me okay? Hello.
Yes, definitely.
Great.
Yeah.
Awesome.
Thanks.
All right. I also just have I got slide jealousy. Sorry about my voice. I'm just recovering from a bit of a cold. Yeah. So thanks for having me here today. I'm also from speaking from Wajak Noongarland, and I pay my respects to their elders, past, present, and emerging. Yeah, so I'm Natasha Hurley-Walker. I work mostly with the Murchison Wide Field Array, which is a low-frequency radio telescope, and I'm a senior lecturer here at Curtin University. And in some ways, I'm a little later to the game than Adam and Vanessa, but in other ways, I've kind of been thinking about this for a long time. So I've pretty much always been concerned with sustainability, and I was very fortunate enough to do my PhD in Cambridge, where you can get around by bicycle. So 100% of the time, my whole working life, I've always got everywhere by bike. And it makes you consider things slightly differently when you're the one cycling and the rest of society is moving around using carbon. You're kind of constantly, especially as a physicist, weighing up the impact of your actions and what other people are doing. And so, you know, while I'm a big bike evangelist, I certainly recognize that there's kind of a hypocrisy there. I'm cycling and then I'm poo-pooing people who are using their cars. But of course, I'm using supercomputers and I'm doing lots of heavy data processing with low frequency radio telescopes. Those people are probably just working normal jobs. Maybe they're outside planting trees. So considering that kind of aspect has led me to sort of take a number of actions in my own life. Now, I'd like to say I stopped flying, you know, but the thing is that individual actions don't scale up. We can't all choose to stop flying individually. So what I've been focusing on mostly is collective action and approaching that from the point of view of talking to the public and talking to astronomers. So in 2018, I started testing the waters and incorporating climate change into my outreach talks, which was a really scary step because you know, it's not something on which I actually work, but certainly when you're looking out at the universe, you can't help but be, you know, understand how isolated and small the Earth is and how precious. So I really wanted to bring that sense of cosmic perspective to the public, and I got a lot of really positive reception. Actually, nobody came up to me and said climate change is a hoax and punch me or anything. Everyone was very thoughtful and you know, really. I made people think differently, and they said that it affected their lives. And so I've been sort of slowly, softly being a little bit more open about this. In 2019, I gave this really fun talk on ABC Radio National, which is a sort of dark satire about the pursuit of infinite economic growth beyond the Earth and into the galaxy. And I got emails from all over Australia from people from all walks of life, saying how this made them think differently about economic growth. And I really encourage you to check it out. It's only 12 minutes long. It's quite entertaining. So I was doing a lot of talking, but you know, 2019 was a difficult year for me. Like many of you, I'm a mid-career, like just transitioning from early to mid-career. And I did not have a job lined up in 2019, a series of failed faculty interviews. So I flew a lot in 2019, you know, really, really terrible. But I was every time in an airport thinking, there's got to be a better way than this. You know, I'm just going to this workshop for a day. A bunch of people are flying here for a day. This is madness. This is a collective insanity. So when 2020 happened and, you know, we had all of the impacts that we've seen, I thought, okay, look, you know, I've been softly, it's time to start putting my money where my mouth is. So I joined Astronomers for Planet Earth, and I'm one of the co-organizers of the session that Adam pointed out in his slides, the EAS this year. And I'm definitely going to go along, although it's an incredibly awkward time zone for me, because I'm really looking forward to hearing from all the cool speakers that we've got lined up. And also because, you know, the lack of travel has given us a lot of opportunities. You wouldn't have been able to go to a conference in Europe without having thousands and thousands of dollars. And the time zones are pain, but the time zones are pain if you go, you've always jet lagged. So there's actually a lot of opportunities. My PhD students have gone to so many international conferences, more than any students I ever had before because of COVID. And so one of the real key things that I'm trying to make happen now is for the ASA and other large organizations to commit to normalizing not traveling. So that means instead of an individual ECR saying, I'm not going to go to this, can you please, record the talk for me? Can I dial in? And being slapped back and being told no. Collectively, as a group, we can say, no, we don't need to do all this travel. And all conferences should have good virtual participation options. And so then it's not on the individual to say, I choose to take the hit for my career to save the planet. Instead, it's everybody, that decision making is normalized. And I think, sorry, this cold is, I need a cough every so often. I think that will have a big effect because like my students who couldn't go before and now they can, I think that there's a huge untapped group of people who have been able to get access to these meetings over the last few years and they wouldn't have otherwise. And I think if we try and take it away from them by going back to just flying everywhere, that's going to have a lot of pushback. So that's one of the big things that I'm working on is this kind of collective action. I basically, there's now a statement on the ASA website about the ASA committing to a sustainable future, which includes renewables for all our supercomputing resources. And I just wrote that in like 10 rage-fueled minutes, and we did a few edits, and now that's up on the website. So yeah, basically I'm here to say, your voice matters, and if you care, you can make a difference by joining other astronomers and then arguing for collective changes. I have a talk about this and a lot of other things on the topic, and also a bit more stuff about astronomy into the future and economic growth that I gave in my IAU talk last week. So there's a link there as well where you can check that out. That's a sort of 45-minute talk and then a few nice questions afterwards. So feel free to check that out if you'd like to hear more. Thanks.
Thank you very much, Natasha. And thank you for still coming and speaking to us when your voice is doesn't sound particularly comfortable, but thank you very much.
No worries.
Very much appreciated. So I should have mentioned at some point, if anybody has a question that they'd like to ask the panelists, either put a comment in the chat or to make sure that I notice and pick on you, please raise your hand. In the meantime, I have some pre-prepared questions that I would like to put to you. So while people are putting comments in the chat, I see there was actually already some. My first question to you is, how have you noticed the attitude of the Astro community changing regarding climate change over the course of your career? And anyone can take this. This is a question for the floor.
I can tell you my experience if you like. From all the people I've interacted with, I've not had any direct negative pushback about taking action on this. I think when the conversation started a couple of years ago, there was a little bit of like initial, oh, we're talking about this now, like, or shock, if you like, in having the subject brought up in sort of formal settings with an expectation that something gets done about it. But that's probably just because it would have felt like it came out of the blue. And once people kind of got over that shock and realized that nobody needs to take any of this stuff personally, and this is about collective action and doing good. Yeah, I think by and large, everyone has been positive, and I've only seen people become more positive in their attitudes about it. And a lot more people are talking about it now. Like it's a standard corridor conversation. I feel like I talk about this stuff more than I do the simulations I work on, for example, at work now.
Yeah, I was going to comment that I'd say it's always been the background of like generally most people I know accept climate change, accept that something needs to be done, but it's the surprise, and that's changed, that we as astronomers have any practical say in how we can do something about it. that I feel has been the biggest change, and that's starting to really percolate, as you can see in this discussion. It's not just we should do something about climate change, it's what can we do, and what's the best approach for particular problems that we are trying to address. And that's been the biggest change, so I think that's great. And hopefully it won't be what can we do soon enough, it'll just be are we implementing it the best way? Is we get to the point of we're implementing it, we're doing it, and are we doing it the best way? And that'll hopefully be the next discussion in the next couple of years' time.
I'd just like to add to that while at my level, like, sort of our generation, perhaps, I've seen plenty of, enthusiasm and support. A few people going, we're all going to die anyway, so who cares? But on the most part, people consider it a problem and they think it's appropriate that we act. I would say at more senior levels, I've had more pushback. Things like the government will sort that out. Other scientists care about that. You should just focus on writing papers. But one of the arguments that I made in my IAU talk, and I think that this is an important thing that is going to force their hand, is public perception. So the general public is now beginning to consider climate change a serious issue, an emergency, a crisis. You saw people on the streets in 2019. If we don't take action, and in 2022, 2023, we're using 50% of the supercomputers, and we're just casually creating, enormous amounts of carbon pollution, and we've never once acknowledged this as a problem. That sentiment about funding astronomy, about looking to the universe, that can all change really quickly. And instead of looking like people who care about the planet and are helping the public, we could look like, very arrogant hypocrites. So I think it's really important to start thinking about this now, just in advance of the public sentiment, so that we're in the right place if we want our field to be funded anyway. And of course, for the survival of the species.
Yeah, I mean, I think it's pretty well covered by the previous answers. I would add, like, similar to the Natasha, that often the decisions we make in astronomy, like how astronomy pans out, is made at the highest levels, so management and senior people. And they're also the people who had the most different career paths to what we had, right? Because it was a lot of travel. It was taken for granted that was how you built an astronomy career. So it's really about working hard to convince the people who are going to make the decisions about how we conduct astronomy that this is important to the next generation of astronomers, and it's something we need to see reflected in policies, both at the institute level, but also at, say, the governance of astronomy in Australia and worldwide, as well as the government at some level. But yeah, like, I think it's, like everyone has said in their talks, there's a limit to what we can do individually. Like, we need the institutional backup, and that's still coming. I think that's, the conversations at the individual level are much more progressed now, but the institutional backup to support those policies in action is still in progress.
Can I just raise one point where an individual can make a difference to some extent, right? I know it's a bit silly, but if everybody does make really efficient computing, then you can also probably do your science faster, and also you will reduce the energy consumption. Hopefully, if everybody does that, then you can have even more science done. And that's some way that, I mean, obviously in the practical terms, I'd be like, bike if you can, do stuff in your own life. But in terms of work, obviously you have an office space. If you can power down the office space, there's small individual contributions. They don't do a lot, but if we all cumulatively do it and we all try to move in that direction, at least we'll be thinking about it as a part of our policy, because it's kind of a habit. We're always trying to think, oh, I should turn off power. I should try to make this efficient, not consume silly amounts of energy. It's true that I guess for some people, maybe in the older generation, I have heard once renewables it takes over, it'll be fine, and you don't have to worry about how you run your supercomputer. But we should still always run with the most efficient thing we can, because try to make sure that stuff is efficient and don't consume that much power. If you're consuming power, even if it's renewable, there's limited finite power. Have a system that doesn't consume that much. Still better.
That's a very good point, Pascal. And thank you all for your brilliant answers to that question. I think there is a question from Moritz in the chat. I'm not sure whether it's been answered or not, but Moritz, would you like to raise this question and bring it to the panel, please?
Hi, can everybody hear me?
Yep.
Yeah, so I raised this question because I was remembered actually by some talk about like industry at one of the OSPREF retreats, and there was a guy basically who made it his career to think about thermal coupling of different thermal systems, and said, if you have an ice rink somewhere and in a pool somewhere next to it, when the heating and cooling systems should talk with each other to be more efficient. So my question is, obviously we produce a lot of excess heat with CPUs, and naturally we need to cool them somehow. So obviously it seems trivially true that you should be able to use excess heat also to heat buildings in some way, to reuse that in some extent. Is there much that is being done about that, or do we just blast out warming out of the supercomputing center?
So I can at least raise the comment here that it is tricky in Australia, just because the excess heat is typically not really needed a large portion of the year, and this is producing heat all the time, and so then you have to cool it. It's tricky to do. It's particularly tricky, let's say, for the Perth system here, the policy system. It's not that obvious. The example I can think of is that essentially almost the same system that Policy is bringing online is being brought online in Finland. They're having, it's the European Union, they have a bigger funds, they have a bigger machine, but that the heating that goes there is piped back to the town that lives nearby the supercomputer, so they get heated water. They have a hydroelectric dam nearby, so what's being in terms of carbon footprint, there's obviously carbon footprint producing a hydroelectric plant, but once it's there, it's not really producing any carbon emissions. And so they have a reasonably green system being powered. And then they also make sure that the energy that's produced by that system in form of heat is being reused. It is being thought of in a bunch of places where it really is kind of viable. So if you run it in some of the colder climates in the world, then it's really useful. And also, obviously, in colder climates, the heating is less of an issue, because you can just kind of, when you're doing maintenance work, you could kind of just open doors and let the system cool naturally. You don't have to use cooling systems, but that's very difficult here. And the example is like, so the Policy supercomputer uses groundwater, but it's just groundwater. So it's just heating the groundwater that is in a vast aquifer around Perth. That hot water isn't piped into any particular place. It could be piped into the ARC building that lives nearby, but then it would be sort of lukewarm water. It's a question of whether it ends up being useful. Obviously, if you're heating rooms, warm water running through pipes is a kind of good way to dump heat, but that doesn't happen to be the case here. So it's kind of just tricky geographically here. There's also reasons why that other systems are really looking to try to think, where can we place something geographically that could make use of the heat that's being produced by the system.
So
sorry, just something that hasn't been
thank
mentioned.
you for the answer. I was just wondering, should supercomputing facilities then just generally live in colder climates?
Yeah, I know. This is a hard bit, right? So the example could be Singapore. They have supercomputing. They typically buy supercomputing elsewhere, but if they have it in their system, there's nothing they can do. It's a tropical climate. They're going to have to cool it like crazy. The excess heat isn't really useful to anybody. The cooling system that's cooling the system could be circulated in offices and other stuff, but it's super hard to make use of the heat that's produced by that system in a fashion that ends up being easily transportable with a lot more infrastructure, and then also a useful case. So it's just tricky. It's really hard.
Okay, thank you.
Just wanted to add the point, which hasn't been said explicitly yet, that the cooling of supercomputers is the bulk of the power requirements. It's more than what's actually needed to power the CPUs a lot of the time as well. So this is why this conversation is so relevant. At least that's my understanding.
Yeah, so that's why also, if you can have stuff, I mean, GPUs run pretty hot, but if you can have a lot of compute living in the GPU and you only have to cool that thing, then you require less cooling overall. It might require a bit of heat, but and there's examples that are in Perth, like Doug. They have essentially a cooling system where it involves oil. They're very, very limited in the actual CPUs they can use for their cooling system, so they can't just use a wide variety of compute. So that makes it really tricky. But they have a cooling system. It doesn't require lots of fans. It's quite bespoke. It is kind of cool. It probably can't scale generally to most other type of architectures. There's not a lot of things you can actually just immerse in the oil that they have. So there may be changes as we go along, as the liquid cooling by something other than water comes into play. But it also, in this case, it's baby oil. It's a type of petroleum. So you have to extract that petroleum for that type of cooling. it's not necessarily a huge deal, but I mean, it's not like it's completely carbon free, because you actually have to really use petroleum in that case.
Thank you. This is all very interesting. Is this an argument for just not building supercomputers in warm countries? Can we just put them in cold places? I'm sure there's an argument for, I mean, you must have to have them nearby in order to make sure that you get all of the funding that you want from your government. But
I mean, money comes into play, but the bigger thing is data. So if you have things that produce lots of data, and that's the SKA and like ASCAP, MWA, they produce lots of data, transporting that data, powering the communication network is very costly if you have to have high connections like frameworks. And then let's say you want to transmit it to a supercomputer that lives in Hokkaido, Japan, where it's colder, then that's still going to require quite a bit of energy powering the transmission. And it ends up being ideal, but maybe infeasible, because you don't have infinite data transfer rates. So that's a serious limitation.
okay, well, that's a shame, I guess.
Yeah, I wish it was that simple.
Ilya has had his hand up for a while, so do you want to ask your question, Ilya?
Sure. By the way, just a complete aside, but a silly comment on something Pascal just mentioned about the data, which is that when the first NSF proposal went in for LIGO, the gravitational wave observatory in the US around 1980 or so, it specifically included the line item for a courier to carry data from one LIGO site to another every night, so they could combine data between the two LIGO sites that were separated by several thousand kilometers and do a coincidence analysis, because well, that's one way to carry data. You just fly somebody with it. I'm not suggesting that's a good idea. Don't get me wrong. Or that we should go back to that. I had a question about, I guess it's actually mostly about something that Natasha raised, and it's this idea that if we sort of try to, partially address some of these issues by kind of policing ourselves, for example, saying, okay, we're not going to organize as many conferences, or we're not going to travel to as many conferences, for example, or maybe we're not going to use as much computing. How do we make sure this is equitable, in the sense that, for example, the decision-making is likely to be largely in the hands of those who are more senior in their careers and maybe already have the benefit of well-established scientific networks. And if the senior people decide, okay, that's it, we're not having any more in-person conferences, well, they might be fine because we already have the networks in place. But let's say our starting students won't have the same opportunities to develop those networks that we did over the past dozens of years of attending conferences. So how can we make sure this is not harming the people who are still early in their careers?
Okay, I have a couple of answers to that, and then I'm definitely handing to Vanessa. But the first things I would say is that, yes, it's definitely an equity issue. And that is something that we actually really definitely have to address collectively then. It cannot be an individual action. So, we can lobby people like the ASA or the IAU, or, even better, all of the different astronomy societies to formulate policies that allow travel, contingent on career, right? So if you can make a good case for that that travel, then you get the funding, or you're allowed to fly, or you'll reduce the tax, or however the policy is formulated. I'm not a social policy expert. Now, of course, the issue there is if the ECRs are all allowed to travel, but the senior professors don't, the senior professors are the ones with the jobs, then it doesn't really matter if the ECRs travel, because the senior professors won't be there at the same conference. So you have to work this out really collectively. You have to coordinate. Perhaps it's worth once every 2 or 3 years having a big in-person meeting, and you always make sure that any ECRs who need to go can go, but you do encourage people who have funded positions to go as well. It could be a bit more intentional than it is at the moment. It's essentially like efficient computing, right? Instead of just saying, let's just have a conference every year, every few months, anywhere in the world, somewhere fancy, and whatever happens, we make it more intentional. You have networking sessions that are designed to connect people together. You register those intents before you have the conference. You know, I think a lot of it is just sort of selection bias from, as Vanessa said, the people who've already been through this system. They think it's just the way it has to work, but we could design it to work better for ECRs. The other thing I would say, and this is sort of tangential before I pass to Vanessa, is that we are not alone. We're not the only scientific society in the world. And I think that all of the other scientific societies will be facing exactly the same problems. So the coordination amongst astronomers is something I'm trying to work with in Astronomers for Planet Earth. The coordination amongst astronomical institutes in Australia is something I'm working with through the ASA. But my other angle of attack that I'm only just starting out on is coordinating with other scientific societies to try and, you know, come up with good concepts for how this can work going forward. We don't have to do it all on our own. Now, I'd really love to pass to Vanessa if she has any thoughts about this, because this is very much her domain.
Thanks, Natasha. And I agree with everything Natasha said. I think, like she pointed out, there's lots of different fronts on which we can address this. So like similar to Natasha, I'm trying to engage with this conversation in a lot of different places, anywhere from I'm on the exec of the EMCR forum, where the forefront of the conversation is really about how do we set up Australian science, so beyond astronomy, to work best for EMCRs in the future. And so in that role, I think a lot about how we can still be more digital first and sustainable, but also make sure those opportunities are there for EMCRs. As well as, so within, our institutions, I know Natasha's worked a lot within Curtin, I'm talking a lot within CSIRO strategy. So I think one element is we can set good examples as institutions can say, being aware of these concerns, we don't want to build in inequity. We don't want to promote more solutions that are going to make it harder for people worldwide. As long as we know that these are the issues there, you can start to mitigate them. So, and other solutions are saying, well, we want to travel less, but we want to also have these opportunities for people to build networks. So you can have in-person events that are focused just on networking, because that's what's effectively done in person. Or you can trial different kinds of styles of networking, but you really have to get buy-in from the senior people who need to be, who are maybe going to serve as the mentors in this space. So one of the other things we've done from the TFOM angle is, it's not always just like, some people don't need to be convinced about the benefits of virtual or remote technologies or asynchronous collaboration, but others do. So it's also a case of needing to train people and offer demonstrations of these technologies to show their value. So those are some of the elements we're thinking about, but as you go to things like virtual and remote, you can start to bring in other accessibility concerns, people who don't necessarily have the best internet or the most reliable internet connections, or have power outages. South Africa has issues with reliability of power or internet availability. And so if we're saying that by traveling less and by collaborating remotely more, we're going to be more accessible, we have to be aware of the things that are going to become less accessible. The other aspect is also to do with accessibility, like in terms of people being able to hear easily or see easily. Some of that is cultural change, but it's also things where technology can help, like with captioning or stuff like that. So it's like there's a lot of shifts we can do, but we have to make sure that we identify what the risks are, like ECRs getting harmed in their careers because of changing the culture, and work really hard to get people at all levels of decision making involved in that. But I don't know if Pascal or Adam want to add to that as well.
I can at least add I was going to raise the devil's comment, which is the devil's advocate, like planes are going to fly anyway. So if you're not on that flight, that plane flies, your weight has a marginal impact on the fuel consumption of the plane. So I know this is the reason I bring this up is because it is a point that is raised all the time about, well, the astronomical community is small, and almost also generally all science communities are small. Even globally, there's not a lot of scientists. Most of the plane is taken up by people working for corporations and working at company. And I think the idea, of course, is, I don't know what other people think, but I think the fact that if we do it collectively and other science groups do it collectively, or corporations will also start doing this collectively and host virtual meetings. And so there will be an impact of reducing the number of flights and reducing the carbon emission from flights. But perhaps someone else has a different view. And it's a question that I know is asked of me when I raise the fact that people shouldn't necessarily be flying as much as they would like to, if they are in a position where flights are paid for by a company or an institute.
I've got two things I'd like to raise that relate to these previous points.
Can I just jump in a second, sorry, and just say Natasha has to leave for school pickup. So just wanted to say thank you very much. And yeah, it's been great having you. And we should hopefully wrap up just 3 minutes after you leave, so you won't be missing too much.
Great, thank you. School closes in 3 minutes, so cheers. And Adam, tell me your answer later.
Bye. Okay, sure. See you, Natasha.
Okay, sorry, Adam, you go ahead.
Right, when it comes to quantifying your own impact, you could, there are exact ways to calculate that, but I think once you've calculated what your own impact is, whether that's your contribution to a flight, multiply that by 8 billion, because you're not special. So if you have if you think it's okay for you to take a certain action, I think you are implicitly saying it's okay for everybody else on the planet to take that same action. So the true effective impact of what you are permissing is 8 billion times what you do. So 8 billion times one contribution to a flight is a hell of a lot. And that doesn't just apply to flights, that applies to everything. And that's the philosophy I try to apply in taking considerations of things that I do in my life now. I also wanted to share an anecdote on with regards to career progression. But I need to preface this by saying I come from a place of significant privilege. I was incredibly well supported during my PhD to be able to travel. I think Darren's on the line. I owe him a great deal of gratitude for affording me the opportunities I had as his PhD student. And also as a postdoc, the same thing. I've had incredible support to be able to travel and do the things that I want to do. And that probably has benefited my career up until this stage, although that is very difficult to quantify. That being said, over the last year and a half where no one's been traveling because of the pandemic, and after making a conscious decision to stop traveling even prior to that, as for sustainability reasons, with the meetings I have attended remotely, I have made some of what I consider to be the most meaningful connections with colleagues that I have ever made. So well in above of what I've made with people in face-to-face meetings. And maybe that's just because it's it's with the pretense of that relates to a subject that we're passionate about. But surely that should be happening at conferences anyway, you would think. So there are still important connections that you can make and meaningful ones that you can make in remote meetings when they're set up the right way, which is why the stuff that Vanessa does is so important. That being said, if I were to put myself in the position of a young, new PhD student now, would I have the same level of confidence to build those connections? I don't know. And that's, again, a really hard thing to quantify and probably quite personality specific. So that's just an anecdote. Take that for what it is. That's by no means to say that it's easy.
Yeah, I absolutely agree with Adam. And just to weigh in there, I think that's where, those of us in supervisory roles can really do what we can to support the next generation of students and postdocs. Like there are, I think Natasha touched on it earlier, there are so many opportunities that open up when we suddenly say, oh, it's not just about the walls that we're within, we can collaborate globally. We have an honors student in the Flash team right now, and she just presented at an international conference during honors on the work she's done that should have been in Poland. She wouldn't have gone there, like I wouldn't have gone there if it had been in Poland. So it's about, supporting students and postdocs to recognize those opportunities. I think the other place where we really would like more voices, so people here, is, we from the TFOM side, from the remote meetings and how we work and how we define the future, we actually need more voices from the next generation of scientists. So if you are interested, please get in contact, because we would really like to have you involved. We don't want to be making decisions on your behalf without your input, and it would be really good to help shape the solutions that we design to have that.
Thank you very much. I just wanted to say that if any of our panelists have any links they wanted to share, so maybe the link to that website, we could maybe put it on our ANITA workshop website.
Absolutely. So yeah, if anybody has any slides, or I've already put on the slides, for example, from this morning's or earlier session by Greg and Bernard, and I'm going to add Vanessa's slides in a moment. And yeah, if people want to send me anything, it's ilya.mandel@monash.edu. I'll happily add any information to our website. I'll copy the link over in a second. It was somewhere in the chat window, but I'll copy it in just a moment.
Okay, awesome. I think we have come to the end of our allocated time slot, which is a shame because I have so many more questions, and I'm sure everyone else also has more questions. I don't feel like we've come up with any like answers to the, the climate emergency just in this brief hour and a half, but certainly started a lot of good conversations. So thank you very much for that. Does anyone have any final very quick questions just while Ilya is finding that link? If not, we're just going to put a little applause react for our panelists. Thank you very, very much. And hopefully see you all at the next ANITA workshop session, which is, Ilya can remind me when that is.
Isabel, thanks very much again for sharing this, and thanks to all of our panelists, and we will reconvene in a week, same Zoom link, coming our way from Paul and Rebecca. So looking forward to seeing you next Thursday. Thanks a lot to everybody.
Thanks, everyone. Bye.
Bye.